Okay. So at last we finally started conduction, and we derived the heat conduction equation for conduction, the energy equation for conduction in Cartesian coordinates, and we saw the three types of boundary conditions. As and when we come to the sphere and cylinder, I will give the governing equations for cylinder and sphere, but I deliberately and intentionally avoided some complicated mathematics and algebra in deriving the energy equation. I assume that it is incompressible substance and all that. So I could have taken that it is compressible and then proceeded with the whole thing, and then I could have written the TdS relations, TdS equal to dH minus VdP, then dH is equal to H equal to Cp into T, dH is equal to Cp dt, and then finally I have to invoke the continuity equation and then all that. So but I avoided all that because that is not central to this course. We are not worried too much about conduction in a compressible medium and all that. That is why I made it very simple, so that it is a form which is easily understandable and it is palatable to you. Now we will quickly review some basic problems. Okay, we have still 7 or 8 hours, so I will try to review one dimensional problems, two dimensional problems with a perspective which is not usually given in a first course, right. So you will see it as it goes along. We will do a phase change problem and also two dimensional method of separation of variables and finite difference. So whatever is possible in 7-8 hours we will have to pack. So it will be packed, and it will be somewhat different from the earlier part of the course in which we will not be able to solve examples for each and every case. Okay, that pace will not be there. Suddenly there will be nonlinear increase in pace, but it is okay since it is only conduction and most of the material is already known to you. I hope you will be able to tolerate it. So it will be somewhat fast. So now let us consider the plane wall. So the one dimensional plane wall is a classic is a classic system which is studied in conduction and heat transfer because it has got numerous applications. Okay. Examples: what should be the insulation on the furnace? What should be the insulation in experimental setup involving a phase change material? One of my students is doing. What should be the thickness of the cork so that you do not want any heat transfer from the back side, right. Okay, what should be the insulation in an air conditioned room? What should be the thickness of this thermocol false ceiling to reduce the heating load on the air conditioner and cooling load on the air conditioner and so on. So insulation design is a very important example. Then fin system is also a plane wall. I use extended surfaces to increase the heat transfer rate. Nuclear fuel rods. Okay, if it is a circular rod, then it may not be a plane wall. Suppose it has got a rectangular cross section and so on. It is not a plane wall, it is a plane geometry. Okay, there are various applications. Okay, the examples are far too many, applications are far too many, where one dimensional steady state is still very important. Okay, now let us consider a simple problem. Okay, so this is okay. So here there is a fluid which gives a heat transfer coefficient of H1. The free stream temperature is T infinity 1. You can say that this is basically occurring at the wall of a heat exchanger on both sides of which there are two fluids with different temperatures which are affording different heat transfer coefficients, right. This is the common situation in convective heat transfer. There is a solid wall, there is a fluid flowing past it. Either the fluid is moving and the solid is stationary, or vice versa. When the airplane moves, the fluid is stationary and the solid is moving. Once there is a relative motion, a convective heat transfer situation is set up. Now T infinity 1 is greater than T infinity 2. T is a function of okay. So there is no heat generation, T is a function of x only, right. So what is the direction of flow of heat? From left to right, Qx, small q is watts per meter square, that is a flux, okay. The challenge is to compute the temperature distribution inside the solid and also to calculate what is the total heat transfer from the solid to the wall, I mean from the solid to the fluid, okay, right. If you can find out what is the heat transfer from the fluid on the left side to the wall under steady state condition, the same heat is conducted through the solid and it is convected out from the fluid on the right side. Therefore, we can say that the solid effectively acts as a medium which promotes the transfer of enthalpy or heat from the fluid on the left hand side to the fluid on the right hand side. Under steady state conditions, some heat is transferred. Now you may ask me, sir, this temperature will increase and all that. That is not central to our understanding here. These are all the T, so these two are large reservoirs of heat, so that even if this heat is dumped, T infinity 2 does not change. That is the belief here, okay. So the heat is transferred from the left side fluid to the right side fluid through the wall, right. So it is steady state, so Qx will be constant. Now we have to write the governing equation. There are various ways of doing it. I can take an elemental volume, so that is I can take a thickness which is dx, I can consider a unit area in the direction perpendicular to the plane of the board, and then do my analysis. Qx equal to Qx plus dx plus Q generated is equal to Q stored under steady state, Q stored equal to E stored equal to 0, heat generated equal to 0, and you will come back to the same governing equation. So this is what is called as a bottom up approach, or I can use my top down approach where I have the general governing equation. I will chop off unnecessary terms and then use only those terms which are pertinent and relevant to the problem under consideration, okay. So doing that, so rho Cp so this is a general governing equation, okay. So what are the terms which can be chopped off? So steady state prevails in the system, therefore the first term is knocked off. I also told you there is no heat generation, right, Q equal to 0, this is knocked off. Now therefore even the del squared can be simplified because T is a function of x only, correct. This is called the governing equation to the problem. So the first step is to identify the governing equation to the problem, any conduction problem. It is an ordinary differential equation for temperature second order in x. Therefore it supports two boundary conditions. The two boundary conditions are available to us at x equal to 0 and at x equal to L. Whatever heat is lost by convection must be equal to conduction at the solid fluid interface. When you apply these two boundary conditions, if you integrate you will get two constants. We can evaluate the constants and get the temperature distribution, but you will be surprised to note that even such a simple problem, when I gave a boundary condition like that, it is not as easy as you think when you do the algebra, because traditionally in your courses on heat transfer the teacher will say left side is T1, right side is T2. Left side is T1, right side is T2 is very difficult to have in practice. Invariably there is always a fluid on two sides whose temperature alone we know, and there is a heat transfer coefficient. Only if the heat transfer coefficient is infinity will the T1 here be equal to T infinity 1 and the T2 here be equal to T infinity 2. Therefore, having a simple system T1 and T2 is very easy to teach, very easy to derive mathematically, but unlikely to be encountered in practice. Okay. Now let us take the general case. We can always take H1 equal to infinity, H2 equal to infinity, and reduce to the simple case which you are learning from high school onwards. Okay, that is Q is equal to K delta T by L. I do not know when you started learning this. Okay, so that is the, but we are supposed to be heat transfer specialists, so we will have to complicate the problem or take a more realistic case of the problem and see what happens. Now the fun starts when you do the mathematics. Let us do it. Okay, so d square T right. So but getting the A and B is not going to be straightforward because I do not know the value of T at two values of x. Suppose I say x equal to 0, T equal to T1, x is equal to L, T is equal to T2, the game is over. I do not know the temperatures. The beauty is I know only the fluid temperatures which are bathing the wall. Okay, so but two boundary conditions are available, therefore it should be possible for us to solve, right. Let us do that. Yeah, now you have to be wary of the sign. dt by dx is decreasing along x or increasing, dt by dx is positive or negative, because the we know that the temperature should go like this, therefore dt by dx is minus, this should be plus, minus of minus is plus, right side T infinity 1 should be more than T1, only then it is possible for heat to be transferred, isn't it, on the second law of thermodynamics. Therefore T infinity 1 must be greater than T1, therefore the right side is positive, so we are okay with this, right. Now you can get dt by d, therefore minus Ka, it does not help me much because T1 also is not known, therefore what is x equal to 0, right. So T1 T equal to Ax plus B, x equal to 0, therefore T1 equal to B, very good, keep it. So this is now 6. Okay. Watch, here I am saying T infinity 1 minus T1, here I am saying T2 minus T infinity 1, to ensure that both are left side and right side are positive, correct. Incidentally, what type of boundary condition is this? It is the Robin condition. it is not Robin conduction, it is Robin condition. Okay, so this is also called the mixed boundary condition, or the boundary condition of the third kind. Okay, so minus k, again minus k, is that correct? Oh, who is not well? Fine. So the two unknowns are, oh Vinay, the two unknowns are A and B. So you have got two equations 6 and 7. Alright, let us do that. Okay, so what do you want, how do you want to proceed? Correct? Shall we add the 2 now, so that the B gets cancelled? Does the B get cancelled now? Yes. We should know why you are doing all this. We are trying to solve A and B, right? You can keep on manipulating the equations. So we should remember our goal. Our goal is to solve for A and B. I can take the A to the right hand side and push the whole thing to the left hand side. Okay, if that is confusing, I will do this. Minus AL, correct? Minus A into, what do you want to do? Minus KA. What happened? Is there a K? Okay. Now we still do not know whether we got lost in the jungle somewhere. So, but based on my experience I know it is a correct answer, but you may still be having those doubts. So, we will have to find out what Q is. Q equal to minus K dt by dx anywhere, it is the same, right. The heat which is entering the left side has to go through each and every station x and come out of the right side, because it is 1D, it is steady, there is no volumetric heat generation rate anywhere, and T is Ax plus B, therefore Q must be equal to minus Ka, very good. I have an expression for A already, okay, therefore Q is equal to still no, I have not solved the problem yet, we do not know the temperature distribution. So, we have come to the first step where we are able to calculate the heat transfer. As an engineer you may be interested in finding out what is the heat which is leaking into the system or going out of the system depending on your application. Suppose it is liquid nitrogen you are storing inside, so the heat leak from outside is what your this thing, or you are looking at some other insulation system, what is the heat leaked outside. Now coming back to the jungle question, whether we are lost somewhere in the jungle or not. So there should be, as an engineer there should be a way of testing, you should have a method by which you test whether what you have done is correct or not. So one quick check would be, if H1 is infinity and H2 is infinity, that means there is a terrific heat transfer coefficient on, if there is a terrific heat transfer coefficient on this side, therefore with very little temperature difference this wall will reach a temperature which is the same as that of the fluid, therefore T1 must be equal to T infinity 1. That happens when you have terrific heat transfer coefficient approaching infinity. Similarly on this side, if H2 is terrific, that is if it is approaching infinity, T2 must be equal to T infinity 2. Are you getting the point? Because after all what is Q? Q is equal to H delta T, okay. So when the H tends to infinity, for a finite amount of heat flux the delta T required will be very less. What is the delta T required? The delta T between the wall and the fluid. So if H tends to infinity, delta T asymptotically approaches to 0, therefore T infinity 2 will be equal to T2, T infinity 1 will be equal to T1, 1 by H1 will be equal to 0, 1 by H2 equal to 0, this will be T1, this will be T2. So you get Q is equal to K delta T by L, which you learned physics from high school, K delta T by L, okay. So now we got the intermediate result, the B is still left, only if you complete the calculation by getting the value of B we can substitute it back and get an expression for T, and I will explain the physical significance behind this a little later after 5 minutes maybe. So let us work out for B. A is there. So let us start from here. Is it a good place to start from? Okay. Oh, okay. B1. What B1? Why did I write B1? Okay. So B equal to okay. So B there is a minus there already, yeah. Oh, that k goes off, I am very happy about that. So minus divided by what else I have left out? I have left out something. So even when you are doing a derivation you can smell, no, you have done JE and all that. As you go through the derivation you know whether it is 24 balls 26 runs or 24 balls 52 runs. You every step you can find out whether you are going to hit the answer or not, right. So okay, if you keep on working in particular subject, whether it's differential calculus, integral calculus, somewhere the middle itself you will know that yes I am getting the answer or I am not going to get the answer. Okay, now I think we are going to get the answer, right. So what is B? We will keep it like that, no, B, let him be like that, he does not deserve any special better treatment. Okay, now T, because it gave so much of trouble to us, so T equal to Ax plus B, therefore did I leave the K here? Is it okay? Oh, here it is okay. What about the A? A has a K, right? Into X minus just hang on Deepak, one second I will complete it, then tell me is there a place where minus has to be changed to plus, tell me. Huh? What? Okay, A is minus, okay. This is the solution to the problem, that is what we propose, we hope it is alright, okay. Where is the plus T infinity? Wait, plus T infinity 1, why the T infinity 1 comes here, no? So we can write it as T infinity 1 minus yeah, please tell me what is there in the bracket. X, correct? X plus K by H1. What are the units of K by H1? They are in meter. What per meter per? Then it's correct, na? Okay. The expression may be complicated and involved, alright, but is it linear in X? Yes, of course it is linear in S, therefore the temperature distribution is linear. If the temperature distribution is linear, dt by dx will be a constant, Q is equal to k dt by dx, and k is a constant thermal conductivity. So linear temperature distribution will give rise to a constant heat flux, okay. A quadratic variation in temperature will lead to a linearly varying heat flux, okay. A constant heat flux does not always assure a constant heat transfer rate if the area itself is changing, for example a cylinder or a sphere. So dt by dr may be constant, but A may be 2 pi r dr, then we are in trouble, so you have to be careful, okay. So you should not work with heat fluxes always, particularly for cylinder and sphere problems. You can work with flux for those problems where the area is a constant like a plane wall, okay. Now, so this is the, now I told you I just took a plane wall, now we have been working, it's 18 minutes, we have been working for the last 32 minutes. So you thought that it is a very simple problem, but this is the general case. H1 and H2 being infinity are the most specific cases. Now we can substitute if okay. So 8, we gave some number, no? What should be the number for this? No, not 9, 9, 15, alright. So this is also asymptotically correct because, and this will be actually T1, this is the linear temperature profile, okay. People working in heat transfer, we call it as the LTP, linear temperature profile. At x equal to 0, T equal to T1, at x equal to L, T equal to T2 for the special case, right. Q is equal to K delta T by L, alright. Now what was your Q? You got this right, correct, fine. Now let us look at the physical interpretation of this, or let us see if there is another way of getting the heat flux, okay, which we got by solving the original governing equation, okay. So I will take the same problem, of course T1 and T2 I do not know, right. Okay. I can use the argument that it is the same heat flux which is travelling from left to right. At every station the heat flux has to be the same, correct. Where else will it go? There is no heat generation, there is no heat stored, okay. Therefore I can say that the Q is equal to, on the left hand side it is equal to H1 into T infinity 1 minus T1, is that right? This is the heat which is entering from the hot fluid on the left side onto the wall by convection. After it has entered the wall through convection, it has to be conducted into the wall, okay. So the Q is also equal to after it is come to this place, it is the same Q after all it is the same Q, therefore fine. Okay. I will use the same thing now. This must also be equal to what is this? Component or dividend or root. Therefore, okay. The quick and smart way of solving it, but it is not always possible to do it. There should be no heat generation and Q must be constant and all that, fine. But if you had using this method, you can straight away get the heat transfer rate, but if you want to find out the interfacial temperatures or temperatures anywhere, what you have to do is using this you will get Q, and this Q will be equal to T infinity 1 minus T1 divided by 1 by H1, you will get T1, then from that you will get T1. Similarly you can use this formula to get T2 and you will have to proceed, okay. So what it essentially means is I have a temperature difference I have a global temperature difference T infinity 1 minus T infinity 2 between the two fluids. There are some resistances to the flow of heat. The resistances arise as a consequence of the finiteness of the heat transfer coefficient on the outside, the finiteness of the heat transfer coefficient on the inside, and the finiteness of the thermal conductivity of the solid. So 1 by H1 can be considered to be the convective resistance on the outside, 1 by H2 is the convective resistance on the inside, and L by K is the conduction resistance. If H1 and H2 are both equal to infinity, then the two convective resistances will evaporate. Straight away you will get a problem, you will say Q equal to my K delta T by L, alright, okay. So this is what is called as the actually there is a, what is a? It is the area of cross section in the direction perpendicular to the plane of the board, so this is called the convective resistance. Is it clear? Now we look at same 1D plane wall. So conduction there is no syllabus, or you have to take the governing equation, I have to keep on solving till we get tired. If 8 hours are over, I will change from paint wall to cylinder to sphere, I will take steady, unsteady, certain things it is possible for me to analytically solve, certain things I will propose charts, certain things have to be only numerically solved. There is no question of syllabus or anything, okay, we will keep on doing something, okay. So, so the 1D plane wall, variable thermal conductivity. So the governing equation would be what is this? Dou by this is not good, okay. So it is 1D. Oh what? Yes. No, I am fine. Okay. So this fellow is 0 because it is steady state. This fellow is also 0, no heat generated. And since it is only d, t is a function only of x, I do not have to put dou. Okay. So we will again start with some numbers. Okay. So it is a wall like this. Okay. So it is infinite in extent. T1, T2, but unfortunately k is a function of x. Far worse would be k a function of temperature itself, which makes it a nonlinear problem. We will consider both the cases, okay. K could be a function of x, that means the material is anisotropic or non-homogeneous, whatever, okay. Now k is a function of T, it is a nonlinear thermal conductivity, that is, see you are trying to get the temperature, the temperature is dependent on the thermal conductivity, but the stupid thermal conductivity itself is dependent on the temperature. So that goes into a loop, that goes into a spin, so that is why it is nonlinear, okay. Now this is okay. So this is the governing equation. How do we proceed? So kx dt by dx, what did I do? Integrated once, correct. What do we do? What is A after all? A negative of the heat minus of the Q. Well, let us keep it like this. No, let us not get into that argument now. We just proceed with the derivation, but you should remember that. What can I do now? Watch, watch, watch. No, 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 wait. Yeah, kx should come on the right, correct. No, no. If you do this, we will mess up. We should not do like this. What do we do now? Dt is A dx by kx. It is more like it, right? Now I start from t, I start from t1 to any t. So I start from 0 to x. Any problem? Finally somebody will give me the value of kx, right. So some experimentalist or some theoretician will give. I won't be so desperate that I don't know what the functional relationship between k and x. Alright, now how do I get a? Yeah, you integrate between t1 to t2, man. So you integrate between 0 to L straight away, okay, to get a. What is this? T2 minus T1. Therefore, A is by 0 to L. Again at each and every stage you should be able to figure out for yourself whether you are proceeding along the right track. A good way to check whether you are proceeding along the right track is to look at what this expression will become if k of x is constant. If k of x is constant, it can be pulled out of both the numerator and denominator. Right side will be just x by L, which is the linear temperature distribution model for the constant thermal conductivity case. Therefore, it is correct. What you have done is correct. Suppose I tell you somebody gives you kx equal to a plus bx, where a and b are given, it can be straight away integrated, you can get the temperature distribution. A minus of a is anyway, minus of a here is anyway the heat transfer rate, okay. So we will stop here. In tomorrow's class we will look at the case where k is a function of t, and we will try to solve some numerical examples and then go to the heat generation constant. How to take away the heat generation is topical because this heat generation takes place in nuclear reactors. How is the heat taken away by the coolant, okay. So I stop here.